Welcome to this video, the 7th video in my series of videos on Cantor's 1895 and 1897 articles on the theory of aggregates and transfinite numbers. Section 7 is titled, The Ordinal Types of Simply Ordered Aggregates. Many of the definitions and concepts in this section are fairly self-explanatory and don't really require me to say very much about them. The first paragraph of this section starts off with a definition of simply ordered aggregates. The simple ordering that is defined on a simply ordered aggregate is shown to be a transitive relation. The terms lower rank and higher rank are not to be used synonymously with less than or greater than respectively. Note that the symbol introduced in point 1, used to indicate which element is lower rank and which higher, must be understood to represent a different order relation when applied to different aggregates. Thus, if M is a simply ordered aggregate and N is a second simply ordered aggregate, then the symbol used in relation to elements of M effectively represents a different relation defined between the elements of M than when the symbol is used to represent the relation between the elements of N. This, strictly speaking, also applies to partial aggregates, since a partial aggregate is a different aggregate to the parent aggregate that it's considered a part of. Therefore, if M1 is a partial aggregate of the simply ordered aggregate M, then the symbol represents a different order relation on M and M1 respectively, though of course we can think of the symbol applied to M1 as representing nothing more than a restriction of the order relation defined on M to those elements of M1, unless that is, we wish to define a completely separate order relation on the partial aggregate M1. We may define many different simple orders on an aggregate, that is, there is not necessarily a unique way of defining a simple ordering on an aggregate. Note that the aggregates R and R0, which were introduced on pages 110 and 111, both contain exactly the same elements, that is, positive rational numbers greater than 0 and less than 1. The distinction is that different orderings have been defined on R and R0 respectively. Throughout the work, the symbols R and R0 will have the meanings that they've been given on page 111. The aggregate R may be described as the aggregate of rational numbers in their natural order of precedence, as in section 9. Ordered aggregate is to be synonymous with simply ordered aggregate in this work. The term simply in simply ordered aggregate indicates that the aggregate has a one-dimensional ordering, and since no other type of ordering is considered in the present work, then we can drop the term simply if we wish to do so. The ordinal type of a simply ordered aggregate M is denoted M bar. Every simply ordered aggregate has an ordinal type, but not every aggregate in general has an ordinal type. This notation is significant because the bar above the M indicates a single act of abstraction. See also the video on section 1 for a more detailed explanation of acts of abstraction. The notation M bar can be compared to M double bar, which as we saw represents the cardinal number of M. The notation M bar indicates that we're ignoring the specific nature of the objects in the aggregate M, leaving an aggregate of general units. We still, however, have the ordering of the objects preserved. To ignore the order as well would be a second act of abstraction. I have to warn, though, that a single bar does not always indicate ordinal type. Sometimes a single bar can indicate a cardinal number for certain aggregates. M bar is itself an aggregate, and can be treated as such, much like M double bar is itself an aggregate. M bar may be considered as, again, a kind of prototype aggregate, which captures the essence of an ordinal type. That is, M bar is an aggregate which possesses those properties, and only those properties, that are essential for the aggregate to possess, which may be said to have the ordinal type M bar. Of course, generally, an aggregate N which has the ordinal type M bar may have additional particular properties, but N must nonetheless have, as a minimum, those properties possessed by M bar. The relation similar between aggregates is a reflexive, clearly symmetric and transitive relation. We also see that two aggregates have the same ordinal type, if and only if they are similar. Compare this with the results from section 1, that two aggregates have the same cardinal number if and only if they are equivalent. An imaging is a certain kind of one-to-one correspondence between aggregates, which preserves the order relations between the elements of the respective aggregates, which, of course, a general one-to-one correspondence may not do. Indeed, there may not even be an order relation defined on some aggregates. Here we see that if we have M bar, an ordinal type, that is, we've abstracted from the specific nature of the objects of the aggregate M, and we abstract from the order of precedence, then we obtain the cardinal number M double bar of M. Therefore, we can imagine M bar as being an intermediate stage between M and M double bar. We also see that Since an imaging is a one-to-one correspondence, aggregates of the same ordinal type must always have the same cardinal number. That is, similar aggregates are always equivalent. The converse, however, is not true. Two equivalent aggregates may not be similar. We've already seen an example with R and R0, although, of course, this would need a proof, which I won't be including here. Using the ideas explained earlier in the video regarding single and double acts of abstraction, it would seem that the symbol at point 5, alpha bar, should denote an ordinal type. However, this symbol denotes a cardinal number. We might speculate as to the reason for this, which may be that since alpha was taken to be an ordinal type, which recall is an aggregate, the objects of alpha have no specific nature to abstract away. The first act of abstraction, therefore, doesn't really do anything to alpha. Only the act of abstraction which corresponds to the abstraction from the order of precedence will have any effect on alpha, and so alpha bar represents the cardinal number of alpha. So the following rules of thumb may be appropriate. For an aggregate M, which is not assumed to be an ordinal type, then M bar is the ordinal type of M. M double bar is the cardinal number of M. For an aggregate alpha, which is assumed to be an ordinal type, then alpha bar is the cardinal number of alpha. For an aggregate which is a cardinal number, then there are no acts of abstraction which are relevant to it. So, for example, the symbol Aleph0 bar would be meaningless, as would 6 double bar. Having said that, the notation is not used entirely consistently, and in section 16 of the second article, a double bar is used several times to indicate the cardinal number of an ordinal type. The symbols 1, 2, 3, nu, and so on will be used slightly ambiguously in the sense that they may be used to represent finite ordinal types or finite cardinal numbers. Which use is intended will usually be clear from the context, and so doesn't cause any real difficulties. We must of course always bear in mind that finite ordinal types and finite cardinal numbers are very different concepts, but due to the similarity of their behaviours in certain contexts, then we're justified in using the same symbols. There's no such ambiguity for transfinite ordinal types and transfinite cardinal numbers, since they behave so differently. We're introduced to the notion of a class of types, which is the method by which Cantor collects together certain, particularly transfinite aggregates. Since it's possible for two aggregates to have the same cardinal number but different ordinal types, then we can collect aggregates together according to their cardinal numbers. Thus a class of types represents an aggregate of equivalent aggregates, or more accurately, an aggregate of equivalent ordinal types. Of particular interest to us will be the class of types denoted by the symbol Aleph0 in square brackets. That is, the aggregate of all ordinal types whose cardinal number is Aleph0. It would stand to reason that since Aleph0 plus 1 is equal to Aleph0, or since Aleph0 squared is equal to Aleph0, that the class of types of Aleph0 plus 1 and of Aleph0 squared are equal, not merely equivalent, to the class of types of Aleph0. The notation Aleph0 in square brackets will therefore be preferred to such notations as Aleph0 plus 1 in square brackets and similar, the latter of which will in fact not be used at all, but it suffices to say that each transfinite cardinal number does have a corresponding class of types. It just happens that the class of types corresponding to the transfinite cardinal numbers A and B may be identical. As a rule, wherever possible, the simplest notation is to be preferred. In general, the class of types corresponding to the cardinal number A is A in square brackets. The class of types of A is itself an aggregate and therefore, by section 1, has its own cardinal number A primed. On pages 117 and 118, Cantor cites several works on these two pages, none of which I have any familiarity with at the time of making this series of videos, so I can't really make any additional comments to what Cantor has already made. Thank you for watching. If you found this video useful, then please hit the like button and subscribe to my channel. You can see more videos on various topics on my channel, and if you have any suggestions for topics for future videos, then please feel free to let me know and I'll try my best to put something together. Don't forget to hit that subscribe button and keep an eye out for new videos being uploaded to my channel.